Okay, I'm going to pick up sort of where I left off on talking about drawing pictures of second-order surfaces. Are there any questions about what happened so far?
What happened?
We're defining these surfaces, second-order equations, which can be written in the matrix form, where this Q is a symmetric matrix, 4 by 4 matrix. And the first thing we did was to try to define what area on the screen this thing covers. And in order to do that, discovered that if you look at it from the side, the outline of the thing lies in a plane. The equation of the plane can be obtained from just the third column of the Q matrix. And then by appropriate fiddling around, you can come up with the matrix Q3, 3 by 3 matrix, which is in the screen coordinate space. XS and YS are pixel coordinates, and this defines a curve, second-order curve in screen space, which is the outline of the object. So this tells us any pixels that are inside that curve are interesting to calculate, and ones outside we need not bother with. In order to find out what the range of values of Q3 that are interesting are, start out first of all looking at the outer loop of the whole picture-making process, the Y scan, and we want to find the maximum and minimum Y which bound the curve. And several ways of solving that, but we came up with a way based on taking the two-dimensional line equation, 0, 1 minus y, which is a horizontal line at the y-coordinate here, y, and try to find out which lines of that sort are tangent to the curve. Tangent to the curve means that the product of the line equation with the adjoint or generalized inverse of Q3 is 0. And so that gives us a quadratic equation in y, and that solution to the quadratic equation gives us the y max and the y min. So next we want to take a look at, for a particular scan line, y is now fixed, and we're scanning across in x. We want to find out what the x max and the x min is within that scan line, because we only need to bother with the region in between those two. Figuring that out is pretty much the same as the y business. We want to come up with a quadratic equation essentially for x, and the two solutions of that will be the range in x. Since we know that y is a constant, y over w in the homogeneous case is equal to this constant value ys for the scan line. We can form another identity which can be plugged into the Q3 equation by saying xyw equals xw times getting ahead of myself here. Something like this. So we get x, ys times w, which is equal to y, and w. So you multiply that 2 by 3 matrix on either side of the Q3, and that'll give you the quadratic equation in x. Not anything real amazing about this. We're just plugging in a constant value for y into the Q3 equation. The matrix formulation just gives us a way of organizing that calculation a little bit. So this whole thing will be a 2 by 2 matrix, which we can call Q2. And that gives us a quadratic equation in x, which gives us the x max and the x min. So the inner loop then starts out solving for these two x values, and then it iterates between those two pixels on the screen. the pixel range on the screen. So that's phase one of the drawing process, which is figuring out which pixels are interesting and just calculating for them. The next step is, oh, yes?
Is that Q3 on the left, is that supposed to be the adjoint or just Q3?
This is the real Q3 here.
It's the real Q.
Yeah. What we're saying is XYW times Q3 XYW equals 0. This is the equation of the curve. And XYW is turned into this thing on either side. And so that's essentially nailing down the y as a constant value, which leaves just x as a free variable, x and w. Okay, the next step is once you get down for each pixel, we want to be able to find out what the z depth is at that point. So we can do comparisons with other objects, second or first order surfaces, whatever you've got. Basically, this again is a matter of just substituting the constant value for xs and ys into the equation. Xs and ys are the screen coordinates of the pixel. May as well leave the w in here for the time being. Generally, you can use a value of 1 for w, but there's a few subtleties on that, which we'll get to in a moment. Yeah, if you have something other than w for 1 for w, you w times that. Let me stick 1 in there, at least for the time being, to make it work, sure. So this is a constant, and these are all constants, so you essentially have a quadratic equation to solve for z, which you need to solve at each pixel, and that gives you two values for z. The near and the far one will be the two intersections of the line of sight through the sphere. You can turn this into a real second-order equation in z, and sort of the same trick as I pulled over here, which winds up coming up with an identity for this to turn it into a zw times q something equals 0. So Q4 is multiplied by some 4 by 2 matrix on either side. Now, the interesting thing to note about this, however, is that certain of the values in this matrix here turn out to be very similar to the values in the Q3 matrix that we came up with before. Now, the only way I know of to prove this is to go through and write the whole thing out as a whole bunch of 10 coefficients and shuffle them around and have piles of coefficients and see how they cancel out and so forth. So rather than bore you with all that, I'm just going to give you a few punchlines, basically, and you can go off and play with it yourself if you're so inclined. Certain parts of this thing turn out to be not too amazing. If you look at, again, a side view of the object, here's the eye. Actually, it's out at infinity looking at this, so the orthographic projection goes back onto the screen. Here's the silhouette plane, drawn a little sloppily. Now, if you imagine a particular line of sight going through here, the position in z for these 2 points is going to come from two things. It's going to be where the line of sight intersects the silhouette plane plus and minus some constant value. That constant value is going to change depending on where you are around on the surface. But it so happens that the constant value that you have here is going to be equal to the square root of minus that mess, the XSYS1 times Q3. This Q3 then was the thing that defined the curve that we had on the screen. It sort of makes sense because Q3 defines this curve so that points that are on the curve, this product is equal to 0. And so this displacement away from the plane is 0. Points that are inside the curve, this product is going to be negative. So minus that is a positive number. You take the square root of that, and that tells you how far this thing is away from the plane. Points that are outside the curve, this product is going to be positive. So minus that, there's no real solution to it. The plane itself we've already got by taking the third column of the original Q matrix. That's the equation of this plane here, the silhouette plane for the thing. And so you can take advantage of the fact that these similarities arise to calculate the z coordinates. Now, in fact, you can do a few other fairly simple things to coalesce some of the calculations involved here by making the following observation. What does C use for a do loop? Do? Or for? For? Okay, I may as well use the modern notation here. Y equals Y max. That's not C, is it? Oh, screw it. I'll use whatever I feel like. Maybe we ought to say min to max to make it a little more sensible. This is the basic structure of the thing when we're calculating stuff down here. We can speed things up a bit by looking at all of the arithmetic in this loop, and anything that has a y in it, any calculations that have y's in them, you can sort of factor out of the loop and calculate once up here on the top. Now, some of the things that you're going to be doing a lot for this, for example, xs ys1 times q3 and so forth, you will be calculating this for every pixel on the screen. I'll be explicit here, xs and ys like that. So what you can do is to take all the terms that are just products of ys and these constant numbers in here and pre-calculate them outside of the loop. So you're going to wind up with a whole bunch of extra values out here. And then inside the loop, the only calculations you're going to wind up with are this whole thing is going to be basically a second order quadratic equation that you'll be calculating for each value of x. And then z is going to be the square root of minus this value, which is the offset of this thing, plus the value that you get from solving the plane equation here as well. Now, the plane equation, again, is ax plus by plus z equals 0. And so when you're solving for z in that, there'll be some other extra values up here. You wind up with an expression basically of this form, where the a, b, and c, and d, and e are various arithmetic applied to the y and the coefficients of the equation and so forth. So this is the basic inner loop of the equation for each scan line. Now, one other interesting thing to point out, I don't know if Nelson mentioned this before last term in section on talking about polynomially defined parametric curves, but if you're going to evaluate something like this lots of times for equally spaced x values, you can use forward differences. Did he talk about that? Instead of multiplying x by x and b by x and all that kind of nonsense, you can pre-calculate a few interesting numbers on here and turn this thing into just a couple of additions. What's the easiest way of describing that? Let's take a look at let's start out evaluating this thing at x min. I'm going to make a little table here of f and x, right? This will be the first value that we'll plug in here. Strictly speaking, you're probably going to move in to the integer values of x that are within the x min and x max boundaries. Integral values of the coordinates are where the center of the pixels are. But the initial x that you use here, on the next pixel over to the right of that, x is just 1 bigger than it was, right? So you're going to be interested in f of x min plus 1. Well, let's plug that into here and see what we get. A x min plus 1 squared plus b x min plus c. A little bit of algebraic prestidigitation on that, and we get, whoops, yes, thank you. Bit crowded here. We get the following thing. Like that, right? The next pixel across from that thing is going to be x min plus 2. Plug that into here, and we get that. Do a little bit of algebra on that, and we get plus, what, 4ax min? Plus 2a squared here, I believe, plus 2b plus c. Is it? 4a squared, that sounds reasonable. Are we making sense? Oh, we lost the c, right. Okay. To keep the audience alive here. Oh, let's see here. We've got x min plus 2. The square of this is x min squared times a. That's that term there. 2 plus 4x min times a, which is that, plus 4a. No squared. Okay. No squared up there, yeah. When I put it down in the second place, I thought I made a mistake in the first place, but okay, are we straight here? Okay, the basic idea here is as we're stepping across an x, you can see that the value of this thing is going to be the initial value we started out with always shows up like this, right? And then this term here is going to be basically linear in x. If we take, say, the difference between the first and the second term, in order to get from here to here, we can just add 2a x min plus a plus b. In order to get from here to here, we can just add 2a x min difference between these two is 2a x min plus 3a plus b, right? Etc. Now, what we're doing here is taking what's called the first difference of this thing. It's sort of like the derivative, except it's the difference between each successive values of the function. And if you were to plot this, you'd see that these things go along in a straight line. I will predict that the next, in step 3, two, 5, yeah. We'll get something like that, etc. So the increment from one step to the next changes itself in a linear fashion. The difference between these two being 2a, between those two is 2a, etc. So if we want to calculate a second-order polynomial in equally spaced increments, we can do the following thing. Make sure I don't erase too much good stuff here. The initial difference that we're going to add is 2a x min plus a plus b. And the second difference is just 2a. Now we can erase all this stuff. So we initialize those 3 memory values like that. And then each step through the x loop, we do the following thing. You use the current value of f you start out with here. Then you say f equals f plus df. And you say df equals df plus ddf. 2 additions is all it takes to go from one pixel to the next here. This is called forward differences. And to evaluate a second-order polynomial, we have 2 of them. To evaluate a cubic polynomial, we have 3 of them, and so forth. This is very useful for making, for example, line drawings of parametrically defined surfaces, where they're polynomial functions like Bezier curves and so forth, because you're going to be crawling along this cubic function with equally spaced parameter values, and that will give you a way of generating these things with just a couple of additions instead of evaluating a whole polynomial at each parameter value. Yeah?
How does numerical inaccuracy affect these calculations?
Numerical inaccuracy can kind of creep up on you on this thing if you use very small step sizes, for example, or if you have a very high-order polynomial or very low precision in your words. In practical situations with floating point numbers and so forth, you're not going to get in much trouble for any reasonable ranges of values here. If you're using, say, scale integers or something like that, you have to be a little bit careful, because the differences and the double differences will start having twice as many and 3 times as many bits of precision that you need in order to keep things from wandering away. Basically, numerical inaccuracy is the sort of thing that you try it this way, and if something fishy happens, then you start worrying about where the resolution is going. So this is what we use to evaluate this function f, which we're going to take the square root of at each pixel, which gives us the z depth. So it's a whole bunch of called linear differences or something like that, a whole bunch of little linear difference engines. You're just adding constant increments to values, or increments to increments, and so forth. Okay, so that's step number 2. How do we find the depth of the object at each pixel? Finally, the third phase of our drawing process is to find out what the normal vector is to the surface so we can do the lighting calculations. Now let me go over here again. Now the normal vector is defined as what's called in the jargon the gradient of the function. which we discovered that for second-order surfaces, we can evaluate this thing by just plugging in x, y, z, w on the point times q this point on the surface times the matrix that defines the surface gives us another set of 4 numbers. These 4 numbers form the plane tangent to the surface at that point. The first 3 coefficients of the plane equation, a, b, and c, are the normal vector, right? Now, the thing you have to watch out for here is that this normal vector has to be calculated in real space instead of the perspective bent space that we're doing all the geometric calculations on so far in order to get the lighting right. So this means that the q that we use for the normal calculation is a little bit different than the q that we used for the geometric calculations. We've got, a little while ago, we split the transformation that defines the object up into 2 pieces. Matrix T and the matrix P. T was the part of it that actually takes some canonical unit sphere, for example, and positions it where you want to go and does the viewing transformation and so forth. P does all the bending in the perspective space and the non-square pixel distortion and so forth. And so it's in between these two that we want to do the calculations. You have one version of Q, which is the perspective version of this. S here is the primitive matrix, which represents, say, a unit sphere or whatever primitive function you're doing. And then PT, so forth, like this, transforms it into perspective space. This is what we did before. The Q in the real space that we're going to do the normal vectors in is the same thing without the P's on. Which is just that part of it. There's a -1 in there, but it might have gotten lost in the shuffle here. And when we calculate a z depth in screen space, we have an x, y, and now a z in screen space. In order to get the normal vector, we need an x, y, and z, but not in screen space, in real space. So the easiest way to do that is to multiply this thing by P inverse. In real space, and multiply then this thing by the Q, real space Q. Which is T inverse S, T inverse transpose. And this will give us the normal vector. It'll actually give us a 4-element matrix. The first 3 components a normal vector, and the last one you ignore. And so you mush these together, and you come up with, finally, this whole mess. P inverse, T inverse S, T inverse transpose, almost the same as Q perspective here, except we just have dropped off the last perspective thing. Now, of course, you can pre-calculate this whole mess here, which gives you a 4x4 matrix, so you have that laying around outside the whole loop. And in addition, you don't really need the final column of it, because you're going to ignore the final element of this 4-element vector anyway. And also, when you have nailed down your y value within the y loop, you can merge that in with this matrix. And so within the x loop, you have xs zs1 times a 3x3 matrix gives you the 3 elements of the normal vector. So the ZS comes from taking the square root of this giant function, and you multiply that in here. Now you can even start making more elaborations on squeezing the blood out of this thing by noting the fact that within the X loop, this XS starts out at the left-hand edge of the thing and increments by 1 each time. So rather than multiply XS by this thing each time, you merge the initial XS into this matrix, and you take the top row of it, and you just add it into the matrix each time because XS increments by 1. So it's just adding the top row back into the matrix. So there's a lot of little bits and pieces that you can squeeze out of this thing in order to compress the code down a lot, or compress the time down a lot. You probably wind up inflating the code somewhat, but little trade-offs like that. Now,
What was the S?
S. Oh, S is the 4x4 matrix, which is one of your primitive functions. Like for a sphere, it's 1, 1, 1, minus 1 on the diagonal. It's, you might have another one for a cylinder that you use as a primitive that you transform around to proper place and so forth. Now, you now know how to draw one second-order surface. Drawing lots of them is not inherently difficult. It's basically the same as drawing lots of polygons. It involves doing all this calculation for several different surfaces sort of simultaneously as you scan down the screen, which means that you have to have an array of matrices Q and keep track of which ones are entering and exiting the scan line. So you have a bunch of spheres on the screen, for example. As you have a scan line going down the screen, you wind up having a list of active surfaces, and they enter the list when the scan line drops below their maximum value, and they exit the list when the scan line drops below their minimum value. And within one scan line, then, you take a look at the active surfaces that intersect that scan line, and as you go across, you keep an x-active list, basically. You calculate the x-min and x-max for when they're interesting, and as you cross that, they enter the x-active list, and as you cross the right-hand side, they exit the x-active list. The same sort of thing as you do for polygons, except it's the limits on this thing are calculated a little bit differently. Yeah?
If you've got a Z buffer, why can't you just do all the polygon or all the spheres in random order?
If you have a Z buffer, you can do everything in random order, certainly. Z buffer, however, is not the only way to do things, and many people, myself included, don't think it's the best way. Now, there's one subtlety in here which is going to come back and bite you, and I had to learn about it the hard way. And that is, sometimes the solution for the visible area on the screen does something not so nice as come up with an ellipse. Notice we came up with, for example, the y value, the y range that the thing hits on the screen from this quadratic equation for y. 0, 1 minus y times q3. Do this right here. Solutions to this thing, I blindly claimed the maximum and minimum values give you the visible range on the screen. Now, that's not always the case. If you imagine, for example, a hyperbola, the minimum value of the hyperbola and the maximum value of the hyperbola are like this. That's not the interesting part of the screen. It's that part, the outside part. Now, this turns out to crop up in real life more often than you might think, because when you're drawing a picture of a sphere, the projection of a sphere on the screen is not always an ellipse. It's motivated by what you might consider a trivia question. When you stand, out in your backyard and you look out at the horizon at night, what geometric shape is the horizon? It's a hyperbola. If we have a sphere sitting out in front of us and we're looking at it, it'll project onto the screen here as an ellipse. That's because the eye is sitting here in the plane that contains the eye is kind of off away from the thing. What we're doing is we're going through a perspective transformation which takes this plane and transforms it to the plane at infinity, and everything else distorts appropriately. So this thing squashes into some sort of weird ellipse in here like that. In general, if you take a sphere through a perspective transformation that takes a plane out to infinity, you can come up with three different situations. If the plane starts out being disjoint from the sphere, you'll get an ellipse. If the plane happens to be tangent to the sphere, you move this thing out to infinity, this thing is going to transform into a paraboloid, because this point is going to go infinitely far off in that direction, and so the cross-section of this thing is a parabola. If the sphere and the plane intersect, you take this thing here, you transform it off to infinity, the back half of this thing is going to go past infinity and wrap around and come in from the other side. So this thing is going to turn into a hyperboloid. This half of the thing turns into this half of the hyperboloid. This half of it turns into that half of the hyperboloid. Now, in fact, if you imagine your eye sitting, for example, here and looking forward, like you were sitting on the surface and looking forward, part of the Earth is behind you and part of it's in front of you, then when this thing projects onto the screen, the hyperboloid will be not quite that shape. It'll be something more like that. Here's the eye out at infinity here. And so you'll get the back half like that, and it will have asymptotes going off someplace in that direction. So as you look forward, you're going to see, here's the horizon here, projecting back onto the screen. And this is kind of what you would see in front of you as the land going out to the horizon. This part up here is totally bogus. That's the part that was behind you. You have roughly the same clipping problem than you had with polygons that were partly in front of you and partly behind you. In that, when you go to solve the silhouette outline for this thing, you're going to get on the screen a hyperbola with two hunks. Which hunk do you want to keep? You don't want to... You get a y max and a y min in here. You can't just say, well, let's go from y min to y max. You have to say, is this the inside part of it, the interesting, juicy stuff, or is it the complement of that? In which case, it's only one of the two pieces of the complement that we're interested in, and which, so, if so, which? Now, the way to detect that is as follows. This thing here gives us a quadratic equation in y. If we plot this value of this function here, we're going to get a parabola of some sort. And we are interested not just in the area between where this parabola intersects the function equals 0 axis here. We're interested in the range in which the value of this thing is positive. Because those are the ranges where stuff is. Now, if the parabola happens to be pointing down parabola, that means you take the two intersections here, and the values in between that, that's all good stuff in y. That's the ellipse case. If it happens that the function looks like this, however, here's the two intersections. And it's this range here and that range there which you're interested in. Those are the two places where the function is positive, and those are the places where the square root exists and the thing shows up on the screen. So you have to take a look basically at the what amounts to the sine of the y squared term in here. That'll tell you if the thing is upside down or right side up. Now, if so, you've got two choices. You can either take kind of minus infinity up to this point, or strictly speaking, the bottom of the screen up to this point, if the thing was on the bottom, or you can take this part here up to the top of the screen. One of those two things is the correct one. How do you determine which of these two is the good part? what you do is, knowing that the thing is a parabola like this, you find the y values at these 2 points, and then you plug that into the Q3 equation to find out what their x values are. So you now know xs1 and xs2, the points, the extreme of this thing. And you plug those into the original Q equation to find out what the z value is at these 2 things. Now, effectively, you take the closer one, but you have to think of this kind of in perspective clipping terms here, is that here is a side view in perspective space, lump and lump like that. Presumably, there's a plane in between here, which is the far clipping plane. This is the thing that either used to be at infinity, and it's now got brought in by the perspective transformation, or it used to be at some non-infinite distance, but still got brought in by the perspective transformation. So if the z is on the other side of that thing, that's the chunk you throw away, and if the z is on the front side of it, that's the chunk that you keep. Now, I mentioned the fact that I had to learn about this the hard way myself. I don't remember if I showed the first day of class one of the Saturn flyby films with Pioneer 11, where we're flying under the rings of Saturn. And so you start out, top view, here's Saturn, and here's its rings. Start out along here in a trajectory. Here's the plane containing the eye point, and it flies in like that, and everything's nice until right about here, as it goes around Saturn, the plane containing the eye intersects Saturn. Now, Saturn's off to the left, and it's moving and getting big and so forth. Nothing real dramatic happens to the shape of Saturn. It started out being, here's the screen, an ellipse off to the side, and it gets kind of bigger and bigger. And you can't see anything dramatic happen when this ellipse turns into a hyperbola. It just kind of flattens out a little bit, except for the fact that before I stumbled across this thing and had the program handle this thing, as soon as the plane intersected this, the program went berserk and put just crapola all over the screen. And so I had to go in and fix this thing up so it was able to detect these 2 cases and operate properly when you got in real close to almost sitting on the surface of the planet. Now, there's still some sort of fishiness in the program, which I haven't yet ferreted out. When this plane is exactly tangent to Saturn, and the thing turns into a parabola, that means that there aren't really 2 solutions like this. This is just a real parabola here, and the top part of it doesn't show up at all. And so what it amounts to is, in this case, this function of y is not a second-order function. In the case where you wind up with a parabolic outline of the things, you plug this in for y, and you discover that the second-order term in y, the coefficient is 0. It's really a linear equation in y. F, y, zing, like that, straight line. So that means the area in which this function is positive, which is the area of interesting stuff, starts at some place on the screen and just goes infinitely far up to the top. Nothing down here below. Right? And so this is a perfectly reasonable thing. So you have to have your program smart enough to detect that as well. Now, as it happens, the program doesn't do that, and I had to get the film finished before going through all the Mickey Mouse in order to figure out exactly why it didn't do that right. And so when I finally filmed it, there are 2 frames missing out of the movie. The one on the way in where the thing goes to the parabolic stage, and on the way out where it goes through. And every time I see that movie, you go in and the thing suddenly goes jerk, and then it goes around and goes jerk like that. And I just about fall off my chair because I'm looking for it and it looks so awful. I've never once found anybody else who's noticed it. And so it's interesting to see how much you can get away with sometimes with animation. The person who makes it always is much more critical of the little glitches and so forth in there than the general audience. So next time you see it, you'll know what to look for. Now, I've just said that we have to worry about this thing in y, in finding the range, y range on the screen, which is interesting. You have to do the same sort of thing for x, for each scan line. In that you can imagine this whole parabolic thing, or hyperbolic thing, just turns sideways if you happen to be kind of on the side of the planet looking out or something like that. And so the curve that shows up on the screen might look something like this, in which case this is the good stuff here. And so for initially when you're solving for y, you discover that, again, it's not only a straight line, but it's a constant here, or it's a parabola that doesn't intersect the y equals 0 axis. So in this case, the parabolic function here solving for y might be always positive. The whole y range of the screen is good stuff, and going off to infinity or whatever. Or it might be, well, in the hyperbolic case, it's going to go off to infinity completely here. And so you have to be prepared to handle that as well. Then, for each scan line, you have to do the same sort of solving here, in that you solve for x max and x min. You don't believe that those are immediately the maximum and minima. They might be the complement of it. In the hyperbolic case, then you have to be able to figure out which half of these two that you want. Now, for cases where spheres are going to be out there and for objects modeled like ants walking around or something like that, quite often you don't get into trouble with this thing. I happen to have a case where I stumbled across it early, but you know, if you want the program really to work for all cases, you have to be able to handle this. Now, there's one little mathematical trick, a representational trick, which I might as well put forth to you here. Suppose we have this equation, and we want to solve this thing for z. I've just been saying solve this for z. We're really interested in z over w, the real coordinates of the thing when the z over w happens. So we mush this together, and we wind up with something like az squared plus 2bzw plus cw squared equals 0. And you put this into the standard quadratic equation, and you get minus 2bw plus z equals minus 2bw plus minus the square root of 4b squared w squared minus 4acw squared all over 2a. Mutter, mutter, mutter. Normal thing here, w times this junk equals z, or z over w equals this junk. This is kind of the standard way of solving it. But this admits of a few singularities. In these cases here where we're going to worry not only if this thing is a real parabola and nice, but if it's a straight line, it's not even a parabola at all. If it's a straight line, we're in trouble. A is equal to 0 here. And we're trying to divide by it, and that's a no-no. Now you can just say, well, if a equals 0, jump off to here and do something else. But to worry a little bit about how close to 0 a is, round off error and things like that. There is a symmetrical way of doing this, which is not bothered so much by particular values that are in here. And that is by thinking of this thing, again, as a homogeneous coordinate system in one-dimensional homogeneous coordinates. Really, the real number we're looking for is z over w, but we're going to write it as z comma w. And we can write this thing as a combination of terms here. Yeah. Let me see if I get this right. Right. This is one of the solutions. All I've done is not bother dividing by a directly, but I've just separated the top and the bottom into this thing here. And the other solution is minus b minus whatnot, comma a. Trouble with this is if a is equal to 0, we're going to come up with a sort of a singular case here, because we're going to wind up with 0, comma 0. G over W is 0. B squared minus AC. If A is 0, this is B squared. Up here, square root of B squared minus B is 0, and then A is 0. Nasty. So it's possible to write this in a somewhat different way as like that. The two solutions now are kind of symmetrically arranged. This is the same in both cases. Here we have a C in the front and an A in the front. And you can prove to yourself that this solution here, the ratio of these two things, is the same as the ratio of those two things except the other solution with a minus sign in here. That is, what I'm claiming is that that is the case. One of these things turns into 0 or 0 if A is 0. The other one turns into something more useful if A is 0. And so this is a good thing to have around. If you have a quadratic equation, just solving it by the quadratic formula is not always quite enough. Okay. Now I've gone to a lot of detail in quadratic forms because they turn out to be useful as building blocks for other similar algorithms.
You say that term over there turns into something non-zero if A is 0?
Pardon me?
No, the 2 went away.
The 2's cancel out, I think.
If A is 0, you get minus B plus the square root of B squared, which is minus B plus B, and that gives you C over 0, and that's not too nice.
Well, C over 0 is okay because in this case we're talking about homogeneous coordinates here. Z over W, it's okay for W to be 0 because that means Z is infinite, right? What I want to avoid is having them both be 0. Right? Homogeneous coordinates, it's okay for W to be 0. And they'll both be 0 if you use the other form.
Can you mention what super quadrics are? I just read about something.
Super quadrics are where you have, well, normal quadrics are things like x squared plus y squared equals 1 circle. Super quadrics are x to the p plus y to the p equals 1. P is something other than 2, like 1 or 3 or 18 or God knows what all. And p equals 2 gives you a circle. P equals less than 2 gives you something like that. P equals greater than 2 gives you something like that. P equals infinity gives you a square.
I believe these are also known in the literature as fractals.
No, fractals are something totally different. Zing. Hey, change. Time for a word from our sponsor here. Now, so far we've talked about modeling bigger things as collections, say, of spheres and ellipsoids and whatever. And we've been inherently sort of adding these things together. That is, the net object is the union of the objects that you start out with. There are modeling schemes which people are playing around with, which model things using a more general, what amounts to Boolean operations between solids like this, where you define A and B and C, for example, to be simple quadric surfaces. A plus B, well, A times B, where this means Fortran dot and dot, you know, anything is in the surface if it's in surface A and surface B. This will give you sort of a lens-like shape, right? It's the intersection of A and B. And A plus B, I guess, plus is sometimes used for the logical operation of OR. This will give you the merger of these two objects. Then you can start getting cute with things like what is not A? Well, A is a sphere with the outside of it and the inside. It's a solid sphere, basically. Not A is kind of like the whole universe except for this bubble on the inside. Well, if you take just plain old not A itself and try to draw a picture of it, it's kind of meaningless, right? But let's take B here and A. Yeah, it's easy. It's blank screen. Great. Now, if you take the intersection of not A with B, what do you get? You get B with a little dimple eaten out of it. Well, these things are amusing by themselves, but they start taking in real significance if you imagine a cube or a slab of some sort defined as a bunch of planar surfaces. You can define this thing as the intersection of a bunch of quadrics, degenerate quadrics in this case. One form of degenerate quadric is parallel planes, and so the stuff that's inside it is just a solid slab. So if you take the intersection of three solid slabs like that, that'll give you this brick here. Now let's intersect that thing with an inverse cylinder like that. The inverse cylinder acts like a drill, and it drills a hole in this. Right? And we can start coming up with whittling tools, say. Let's take a plane and intersect it in here, and so we'll just kind of lop off the corner of this thing. And then we'll take this gadget here with a hole drilled in it, and we'll ore that with some other slab on here to attach it on. And suppose we want to make a little fillet in here, then we can put a cube in there and put a negative cylinder on top of that to make a semicircular groove going down here. And so you can kind of glue things together like this just using logical Boolean operations on surfaces and pieces thereof. This is a fairly powerful geometric modeling tool. I know various people who have been dealing with it over the past. And it turns out that there are some fairly elegant algorithms for drawing pictures of these things once you've got the model. Now, I haven't actually implemented this myself. I just had it described to me once by some people from the General Motors Tech Center, and I'm going to try to give you a sketch of the outline of how it works with maybe a few details not quite filled in. Basically, what you wind up having here are a bunch of primitives. And the whole object is defined as a giant Boolean expression, basically. This and that glopped together with not this or this, something like that. And so you can define that as a tree, effectively. You can expand the definition of this thing as a tree. And you're going to wind up evaluating this Boolean expression for each pixel as you go down the screen from top to bottom in the following way. First of all, we're interested only in the areas where these cues are visible, and so you do the appropriate silhouette outline calculation and only worry about calculating branches of this tree where the cues are potentially visible. But within a particular scan line, and at a particular pixel xs and ys, Q1 is going to wind up, say, covering this area. We're again looking from the side view. Z goes like that. So the front side of Q1 is here, and the back side of Q1 is there. Q2 then is might intersect some overlapping area like that. And so we wind up kind of chasing up this tree one branch at a time. You start out saying Q1 or Q2. We want to keep the OR of these two, which means the union of this thing, and so you just hang on to, you merge them together into the OR, right? So you keep that as the front and the back. Q3 now might be out here someplace. Not of Q3, it involves just switching the order of these two. The front and the back kind of change places. So maybe represent that like this. And then the and of this and this will be taking the intersection of these two, which in this case is null. And so this whole thing doesn't show up on that pixel. A little later on down, say, Q3 might actually overlap like this. Not Q3 would go like this. And the and of this thing would wind up coming up with that little piece there. And so you're evaluating all these Boolean expressions for each pixel in order to come up with whatever the result is that's left. And you take the normal vector from that thing and shade it in.
Those last two don't look right. If Q3 is way out on the outside somewhere and then you knot it.
Right, I did something wrong, didn't I? I put Q3 out here on purpose so that it would stick around. Not Q3 would be here, like that. And so this is good stuff and that's good stuff for Q3, going out to infinity. So this and this keeps the whole piece here. Right?
What does it do to the lighting and so on, this whole model?
Well, the lighting doesn't really change. You're only interested in the fragment of the surface that's frontmost.
But what if it's a part of two surfaces, right? Then
The part that you're going to wind up with when you're done here is just one solid piece, and you'll keep the front half of it. And so basically the part of the surface which points to you is going to be sitting on one or the other of these primitive surfaces. Well, you have to keep track of that when you do the merging here.
Yeah,
each end has to have a pointer to the original
where you
surface.
took a dimple out of that thing?
Yeah.
Right, then how do you know whether it's the color of the thing you took a dimple out of or the other thing? I guess you have a concept of what you're whittling with?
Yeah.
And
Each of these things has whatever pointers and lists they have onto it for color or whatever.
And the paint doesn't get scraped off.
Yeah. As I say, I haven't implemented this myself, but you have to sort of keep track for each surface that's in front, kind of where it came from. Do whatever it takes to make it work. You know. Fill in the cracks. Now, this is sort of a generalization of some earlier concepts which people have dealt with in whittling algorithms for just polyhedrally defined objects. Bruce Baumgart at Stanford and a guy named Ian Braid in England originally came up with that, taking polyhedrally defined objects and intersecting them and taking knots and ands and so forth. Mathematically is more convenient because intersecting planar objects is easier to calculate. It's just a straight line. If you want to intersect explicitly two second-order curves, it's not always too easy. Intersection of two spheres is not too bizarre. It's a circle of some sort. But suppose you take a cylinder like that and intersect it with another cylinder like that. The intersection of those two is some sort of distorted, bent thing. And so the curve, which is formed by the intersection of two second-order curves, is at least fourth order and maybe more than that, for all I know. But what we're doing here is doing this thing one pixel at a time, and so that simplifies the matter. Now, one of the things that I had to point out about this algorithm and similar algorithms that deal with algebraic surfaces is that they are in image space, which means that they operate kind of the projection down through the center of each pixel. And so it's somewhat difficult to do anti-aliasing for this because you're not explicitly solving for the intersection between two surfaces. You're just finding out which of the two surfaces the center of the pixel happens to pierce. You're not explicitly solving for the silhouette outline. You're just saying anything inside the silhouette will color in and anything outside the silhouette we won't color in. And so you have to wave your hands and do a few other kludgy approximations in order to do anti-erasing. Now, there's one thing that I want to mention real briefly, I guess, since we only have 10 minutes left, which is another algebraic surface thing, which is the deal that I use for doing the DNA replication sequence. The Blobby atom function. And when the people from Cosmos first came up with this idea, they showed me this picture of atoms or rings of carbon atoms and things like this look like chewing gum all stuck together and said, hey, we want pictures of this thing. And I said, well, let's see. Can we do this with, well, lots of little polygons on here? That's a mess. And maybe bicubic patches, but that's awful, and so forth. And what I wound up doing is defining the shape of the surface more or less in terms of what the electron density might be that generates the surface. If you imagine each atom here as being a sphere with a cloud of electrons at some decreasing density as you go down here, so that the density is of electrons is, in this case, a Gaussian distribution, e to the minus r squared, where r1 is the distance from the point to the center of the atom. That's the amount of density that this particular atom contributes for electrons at this point. The amount of density that that atom contributes is e to the minus r2 squared, and the amount of density that that atom contributes is e to the minus r3 squared, and so forth. So the total electron density at this particular point in space is the sum of all these Gaussian bumps, basically, right? Yeah, that's a refinement which comes up in a minute. But so far we've just defined a density function. The surface itself that you're going to see is going to be thresholded where this density gets greater than some certain amount. So I used the value of 1/2 and adjusted there's actually a coefficient in front of these things to adjust the blobbiness or the unblobbiness of the function. So each atom has a radius. The radius is built into the alpha here. So this gives you a density function for all points in space, where this function equals 0, basically, or this function minus the threshold equals 0. We'll give you some sort of hard shell around these of roughly that shape. So conceptually what you do is scan out the entire screen. For each pixel on the screen, you sum up all these things, plug in the x and y, so you get e to the minus polynomial in z. And what you get then is like that. For each atom, it's going to contribute a little Gaussian bump depending on how far away you are from the atom as z moves away. And so there'll be several Gaussian bumps, one for each atom. The total d function is going to be the sum of these things. And then you threshold that at some point, and where that intersects the threshold, that's the particular part on the surface that's visible there. Now, what I wound up doing was kind of putting a sphere around each atom at a distance large enough so this e to the minus r squared shrinks down to something really teeny. And so you only consider atoms when the pixel is closer to it than that. So you, again, wind up having this entering and exiting list of interesting atoms as you scan down the pixels on the screen. For each scan line, you have a list of interesting atoms that are close enough to matter. And then as you scan across an X, you have the same list. So for each pixel, you wind up with a list of maybe 4 or 5 atoms that are close enough to that ray, scan ray going from the eye through that pixel to make a difference in this thing. And you solve those up. And in fact, I had a third order of sorting in that I wound up thresholding the z values. And so I'd go through and go from the I going back here and only include in the summation the atoms that were big enough in z, or within the right range in z to find. And then this particular value was actually solved for numerically with a Newton iteration that solved back and forth here for the zero of this function by using Newton iteration. Now I got a couple of slides, which when we put the slides up, show the results of this thing. I showed the film earlier on in the course. The slides show a little bit more of the effects that you can generate with this.
Nelson Max showed us some slides that he did of the DNA molecule. Do you know how he did it?
Nelson's are all done with hard spheres intersecting. But he's able to handle lots and lots of them. This is a sort of a test image here, if we can get a few lights off. This is two of the parameters of the process. The alpha that goes in front of there, which is basically the standard deviation of this Gaussian, is opening and closing. And then the threshold value is going up and down. One axis varies alpha, and the other axis varies the threshold. And it effectively affects the blobbiness of where you are here. If you go across the top, you can kind of see the threshold increasing out and out as you get farther away from the object. And going down on this axis, the blobbiness goes on. So you've got two parameters that you can adjust within the program to affect the look effect of these things. Next slide, there's a slide maneuvering device here. Each atom is flagged with a color, and then when you solve the equation, you finally get the point on the surface. You look and you find out which of them has contributed the maximum value to the density, and that's the color that you pick. Can we get the next slide? Do I control that? Or okay. This is a view looking down the axis. This is kind of low resolution, but it's an early test. Looking down the axis of the DNA molecule, it's kind of confusing because this has the parameters cranked up, so we're almost using perfect spheres intersecting here. Now, if you go to the next slide, this has the blobbiness of the thing cranked up so that the atoms sort of melt together a little bit more, and you get a little bit more coherent view of the structure of this thing, where you have the outer helical structure and then these slabs of things going back and forth across the middle.
What makes that so jaggy?
Just low resolution. This is all done with image space algorithms, so that each pixel is calculated just as a projection through the center of the pixel. So it's aliasing, it's jaggy.
So some of these problems with seeing black in the front are due to aliasing problems?
Black in the front, like where?
Like,
this here piece of black is the lighting, because that's the part of the surface that tilts away from the
oh, I see. So, for instance, there's one point right next to the highlight. Goes sort of
that?
Down.
That?
Down.
Yes.
Yes.
That's probably a little glitch in the program. Right at the silhouette edge of the thing, before I got it going, you sometimes ran into numerical problems, because that's where the threshold is just grazing the tip of one of these Gaussian bumps. And the first derivative of the function is 0, and the Newton iteration gets confused. That's since been fixed up. Next slide. Just kind of click through the next few slides, kind of 4 or 5 seconds each. This is another view changing the blobbiness to fill in the goo in between. This is kind of the final thing of the colors that was used for the movie. This is adenine and thymine. And they're kind of melted together to give you a more solid, looks like Cheerios. Next, this is guanine and cytosine, which are about the same. You can see the hydrogen bonds, 3 hydrogen bonds going across here. This is the DNA molecule with the blobbiness cranked up way high, just to see what it looked like, kind of like a worm crawling up a caterpillar. This is a piece of an enzyme. This is just the carbon, nitrogen, oxygen backbone of the enzyme, just to see what would happen. We're trying to design some of the enzymes for the movie. Looked at some real enzymes to see what they look like. Next. Blank slide. Okay, this shows a piece out of the movie with this is the real enzyme. Give you sort of an idea of you can build structures out of this thing, not necessarily atoms, but you can just glue pieces of chewing gum together in order to build these structural forms. And they melt together in this interesting fashion instead of having hard-edged intersections.
How did you get the data for where each atom is and things like that?
The data for the DNA came from the National Institute of Health, which has got a big database on DNA and various enzymes, just a list of the XYZ coordinates of the centers of the atoms.
Now, obviously, you calculated the normals to do the elimination. How was that done?
Normals is calculated by taking the gradient of the function, right? Now, the function itself is the sum of a whole bunch of Gaussians, and the gradient of one Gaussian is just take the partial of e to the minus r squared with respect to x, which is a bunch of square roots and crapola, but it's doable.
How much time?
Next. How much time?
How long did it take to do that?
Pardon me? Having trouble with the slides. Why don't you go ahead and put the film up?
There are no more slides.
Oh, is that it? Okay. I thought I put more in there than that.
How long did it take to do that?
Well, put the film up. It's getting towards 5 o'clock, and so I want to get this film going, then I'll talk over it. This is some early tests to show what happens as these things get closer and farther away from each other. Sort of a liquid drop effect here. Now, this algorithm is not particularly fast. This particular picture here was lower resolution than it took in the order of 5–10 minutes. The DNA movie itself, certain of the frames took upwards of 45 minutes apiece when you had 4,000 atoms on the screen. You're doing a lot of numerical garbaging around with exponential functions. Well, I calculated the exponential with a table, of course, and did all the appropriate optimization for doing the second order. The minus r squared in there means that you're doing a lot of second order surface things. The motions in here were simulated by effectively simulating little springs in between the atoms. Really, it's a different function. It's called a Leonard-Jones potential function, which is what physical chemists use a lot for simulating atoms. The jittering back and forth in here is a bug in the program conceptually. And may as well let this play, and you can watch that. I'll explain what the bug in the program for the jitter is, because it's interesting on how not to do things. Typically, when I make a movie, I set the thing up so I can go through and calculate all the odd frames first, just to see what it looks like, and then go through and do all the even frames later. And what happens is with the test movie thing, it would simulate the thing on the picture system, and the atoms would go gushing around, and for each frame it would stop and make the thing on the frame buffer. It was watching the knobs while you're simulating the thing, and so you could turn your point of view around by twiddling the knobs. Well, while you're in movie production mode, you kind of don't want to have knobs sitting around that might be jostled by accident, which is what actually happened. I did all the even frames. Oh, can you... No, it's already up adjustment. Yeah. Good. This film got eaten up in a projector a while ago, and so I went through and repaired it with splicing tape. It's getting really pretty crappy, and I need to see if I can get another copy of it. What happened is when I did all the even frames on that test, the knob stayed put, and then when I did the odd frames, somehow halfway through, I jostled the knob a little bit, and so the point of view changed, and so each frame was calculated at a slightly different position.
So there was no anti-aliasing?
There's no anti-aliasing done in this at all. I was able to get away with it because it's basically small enough. This was filmed off of a TV monitor, camera sitting on a tripod in a darkened room looking at a TV screen. So the phosphor dots tend to fuzz things out a little bit, and the 16mm film tends to fuzz things out a little bit. If you're as closest to it as I am, you can see little wigglies going along the edge.
So this was 512 by 512?
Right, 512 by 512.
Anti-aliasing would have been hard for the same reasons as the quadrics?
Yeah, it's the fact that you're really solving this equation by a ray piercing through the center of the pixel. You're not explicitly solving for where the silhouette outline is for these things, which would be a real nuisance in this case.
Isn't there a filtering operation that you could do later on sort of...
No, that's a common fallacy, which I'm sure Ed will disabuse you of when he talks about anti-aliasing.
There's nothing that would even approximate?
Not really, no. Basically, once you've sampled the picture before filtering, you've lost the information necessary. I mean, generally what you can do is, filter the crap out of the picture, and it will... You'll get rid of some of the problems. Mathematically, there are ways of representing this, but the only way to do it is basically to make the picture look worse than it needs to as a whole. I mean, we can blur the whole thing by averaging together every 16 pixels or something like that, and you probably won't see it, but it'd be like looking at it without your glasses on, too. Now, you can see when these things come in. This little tail breaks off here, which is a diphosphate bond, and so forth. I poured through all back issues of Scientific American and all the articles on how DNA replicates, and found out where the bonds break and so forth to come up with the proper thing. This thing breaks off and goes flying away. And when this backs off, it yanks a hydrogen atom off of this thing, which it spits out, which leaves a free bond open, so that when this thing comes in and breaks off, the two bonds merge together. This was done for KCET for the Cosmos series, which Carl Sagan narrated last. similar. You can see little white flashes that occur every time the thing welds one of these things in here, which they wanted to show that's an exothermic reaction. Blap there. That was done by taking the appropriate frames out, hauling them into frame buffer, and using a painting program to paint in a little white dot. I was going to try to simulate it with some sort of gleamy, fuzzy thing, but I decided it was time to get the film done, and the easiest way was that. Okay. Next time, Ed, we'll start talking about, well, continue talking about film recorders, I believe.